In this video, I'm going to try and show you how the circle plot works in the DT6 in order to be able to view what's called a circle plot waveform of your data. So the first thing we're going to want to do is find the set of data we want to look at. In this case, I'm going to look at this waveform. So go ahead and hit circle plot. First thing you want to do is make sure that the speed here is the speed of your fundamental frequency. You can either use this to sweep across or type it in here or press this little button and type it in. Here you can toggle Hertz or CPM. I'll just leave it as Hertz. Over here we can see this is the original waveform of the data. For the vertical, in this case, we can toggle between vertical and horizontal. Here we see an FFT of this data. One of the green cursors corresponds to the high frequency of the filter, and the other frequency cursor corresponds to the low frequency filter, so we can use those to move around to get the filter region that we want. I'm going to go ahead and say this is a reasonable region. We can switch between regular, which would be Hertz CPM as a scale, or switch to orders, whatever. I'll just go ahead and use regular. And then here we have a waveform of the filtered version of this waveform. So if this green is here and this green is here, we're filtering between 26.1 Hertz in this case and 660 Hertz. So this waveform right here is the filtered version of this one between 26 and 660 Hertz. We have the same zooming buttons and everything from the rest of DT6. Right here we have this thing which will go cycle by cycle at this speed, so we can see what happens to the waveform. This graph, the way it works is one time round the circle corresponds to one full cycle at 30 Hertz. So basically it represents how the vibration moves as the shaft rotates one full turn. So in this case we can see that for this given cycle, the 29th cycle at 30 Hertz, the vibration follows this path as the shaft turns from here around once 360 degrees. The distance between the black line and the green line represents a G value, in this case of 4.77. We can either toggle between the max value, which will set it to the max that it was in the original waveform, or we can switch it to cursor, in which case that amplitude will be set by wherever this yellow cursor is. So we can move it to wherever we want it. I'll just put it right here. And then in this case now it corresponds to 2.72. As we sweep across here, we can see each cycle you can either toggle here or use this, but we can clearly see here that as we sweep across in the cycles, the vibration always is fairly in the exact same spot. So there's a big hump right here, a big hump here, and a big hump here. And as we sweep across, we see it being in the same spot. If the vibration is relatively consistent in location throughout, we know it's a harmonic of the one-time speed, because that means it repeats in the same location for every once round of the shaft. And we can also count the number of lobes and figure out what the speed relative is. So here we see 1, 2, 3 repetitions at 30 Hertz, which means this frequency is 90 Hertz. And we can see that over here, that if we actually zoom in, we can confirm that the largest frequency here is 90 Hertz. So this is just showing us that. If, however, we had a frequency that was not a harmonic, so something that might be from a bearing or something, we would see as we're rotating around, that frequency or that amplitude would shift all the way around. So it might have a large spike here one time, and then the next cycle that large spike might be here, and the next cycle it might be here. And so it doesn't follow, it's not in a consistent location, which means it's not synchronous to the one-time speed. Another thing that this is useful for is if you have a gearbox with a gear tooth defect. If you have the frequency range within the sensor frequency, you can set the filter accordingly, and you can actually get a rough idea of where the tooth is located, especially if you're using a tack, because then you can compare it against where the tack mark itself is. So you can say, oh, it looks like the tooth is happening when the shaft turns 30 degrees based on wherever that tack mark is. So we go around 30 degrees and here's this big impact. And so that would correspond to your gear defect. I hope this video helps. As always, if you have any questions, feel free to contact us. Thank you, and I hope you have a good rest of your day.